All right, so in this set of class notes, we're just going to continue to explore this idea of parametric equations. And I apologize here, I didn't have this actually in the notes, so in your set of notes, you're not going to see this down here. But what you can do is open to page 575 in your book, and we're going to take a look at this multiple choice example together. So what we're going to do is take these parametric equations, these 6 parametric equations, and try to figure out which of these graphs go along with them. So this is something I definitely want you to pause and try to see if you can figure out which is which here. Okay, so hopefully now you've got your 6 guesses after pausing the video and working through that. One of the things I hope you did right away is understood that you could at least, for each graph, pick 2 of the equations, right? So if I take 1 and 2, I understand that those probably should be going with C and D, because we have this idea of there's a square in the y, okay, and we know that these are parabolas, right? So they're so they have the relationship of some variation on y equals x squared. So I would expect those to go with those, right? I would expect 5 and 6 to go along with B and F, right? Because here the t's are all linear, right? And so we would expect those to be the ones that would actually form lines. And then finally, we know that sine and cosine, by their nature, they repeat themselves, right? And so it would make sense that 3 and 4 go with these ellipses here, right? As for different values of t, you just cycle through the same values of x and y. Okay, but then how do we move beyond that, right? So let's start with 1 and 2 here. With these parabolas, how do I know which is which? Well, one strategy would be just to plug in a value of t, right? So for 2, if t equals 0, that means that x equals -1 and y equals 0. So you could just simply say for which one of those does that happen? Okay, well, or graph D here would have to go with number 2, right? Because it has the point -1, 0 on it. So I could say, all right, this has got to be D. And I could do the same thing over here. When t equals 0, I get x equals 0, and I get y equals -1. Okay, well, that happens with C. Right, so I'm able to figure out which is which there. All right, how about 3 and 4? Well, let's try doing t equals 0 here. So that would be the sine of 0 would be 0, and then the cosine of 0 is 1, so that gives us a y value of 2. Whereas over here, when t equals 0, we get an x value of 0 and a y value of 4. All right, and I can see that with A, you get the point 0, 4 when t equals 0. And with E is when I get the point 0, 2. And then lastly here with the lines, let's try the same idea. So with t equals 0, x equals 2, y equals 3. And here when t equals 0, we get x equals -2 and y equals 3. So this one has the point, it does not have 2, 3, but it does have -2, 3. So I know that B goes over here. And then here, I do have the point 2, 3. So that means F goes with this one. For these last two, though, there's also another way that you could tell. Notice that in number 5, let me do this in a different color because we're getting a little cluttered here. The change in y every time t changes is equal to -2, and the change in x is 1. I'm taking that from the coefficient in front of the t. Okay, well, a change in y divided by a change in x, remember, gives you the slope, right? So we know that the equation number 5 has to have a slope of -2. And that's exactly what you have here. Down 2 over 1, down 2 over 1. So that's another way we could know that 5 goes with f. And the same thing here, I can see that the change in y is equal to 1. Change in x is -2. So that's a slope of -1/2. So down 1 over 2. Down 1 over 2. So another way that we could tell that which graphs 5 and 6 go with. All right, so then building upon that last idea we just talked about with the line, it says find the parametric equation for the line of slope 3/5 that passes through the point 4, 2. All right, so first of all, we can sketch this graph without creating our equation. So I can go to the point 4, 2, put a dot, and then if I have a slope of positive 3/5, that means that the sign of the change in y and the change in x are the same, right? So when I say slope is 3/5, just like we wrote on the last page, we understand that that's the change in y divided by the change in x. So that means if I go down 3, I'm going to go left 5, right? So -3, -5 is positive 3/5. And so with that, I can draw my line, no problem. Okay, but how do we come up with the parametric equations? So we noticed on the last page that I took my information about change in x and change in y, I took it from the coefficient in front of the t, right? Because it's saying as t changes, how does the y value change? As t changes, how does the x value change? So since I know that 3 is my change in y and 5 is my change in x, as I write out these equations, I can just simply say 5t here and 3t here. Okay. Now, again, going back to the previous page, though, remember the first way we determined which was which with 5 and 6 was we plugged in t equals 0, and notice that gave us the point 2, 3, and in this one it gave us the point -2, 3. So in other words, these values out here that are constant, that don't have a t with them, they are giving us a point on the line. So the fact that our graph goes through the point 4, 2 means that I can grab the x value and let that be the constant in this formula. And I can grab the y value and let it be the constant here. So I have x equals 4 plus 5t and y equals 2 plus 3t. So you're taking these directly from the slope, and then these come from a point that the graph passes through. All right, so let's do another example, one that's not a line this time. So it wants us to sketch a graph of these parametric equations here, where t goes between -pi and 0. All right, so let's see what kind of things we get here. So I'm going to make a table. There's a different color there, I think. So we'll make a table, and like we did in the video notes, that means we're going to have a column for t, we're going to have a column for x, and we're going to have a column for y. So when t is equal to negative pi, for x I'm plugging negative pi in for cosine, which is going to give me a negative 1. And then I'm plugging in a negative pi in for cosine here, and that's going to give me a positive 1, right? Because I'd be at the cosine of negative 2 pi. And then let's go ahead and pick some other kind of typical angles to plug in. So negative 3 pi over 4. If I plug that into here, I get negative root 2 over 2, which is about negative 0.71. And then here, I'm going to say 2 times negative 3 pi over 4, so that'll be negative 3 pi over 2, which gives me a cosine of 0. And then we'll try negative pi over 2 maybe. I get x equals 0 there, right? Cosine of negative pi over 2 is 0. And then I get the cosine of negative pi, which brings me back to negative 1 again. All right, so then let's do a couple more at least. Negative pi over 4. So that's root 2 over 2, which brings me back to 0.71, and then back to 0 in the y. And then finally, when I go to 0, that'll be a 1 for the x and a 1 for the y. So you can see that all my values here are between negative 1 and 1. So instead of using the each grid mark as a 1, how about we change this up a little bit? So how about this becomes negative 1 here, and this becomes 1, and this can become negative 1, and this can become 1, just to make it a little easier. All right, so we can plot these points now. X is negative 1, y is 1, when t equals negative pi. Here we have x being negative 0.71 and y being 0. So negative 0.71, this is negative 0.75, so it's just inside of there. And then down at the bottom, 0, negative 1. And then 0.71 puts us right about there. And then 1, 1. All right, now what you might need to do is plot a couple more values somewhere through in between here to see a little bit better what's going on. But with this shape even, you might be able to make a pretty good guess that what's happening here is you're getting a parabola. Now, how do I know that that's the case? How do I know that I really should be getting a parabola here and not something else? So remember that what we can do is what we call eliminating the parameter. So our goal is to go from these two separate equations to an equation that's just got y and x in it. So we want to get rid of the t. Now that can be kind of challenging to do when you have trigonometric functions of t. So what you want to think about is, if I already have x equaling the cosine of t, is there any way I can write this so the cosine of just plain old t shows up? And what I would hope would jump to your mind here is that this is a double angle formula. And I can write it as the cosine of t if I say 2 cosine squared of t minus 1. But this cosine squared of t, let's not lose track of the fact that that is literally just the cosine of t squared minus 1. But we already know that x is equal to the cosine of t. So that means this is 2x squared minus 1. So we can now confirm that yes, this is a parabola, because when I eliminated the parameter, I was able to make it look just like this, y equals 2x squared minus 1. All right, so in example 4, this one asks us to parameterize, or in other words, write the parametric equation for the equation y equals 3x to the third minus 4. Now this is going to seem like a really silly answer to the question, but what I'm trying to do is kind of demystify this parameterization a bit. When we say parameterize, all we're going to do is we're going to try to write this as x equals a function of t and y equals a function of t. Now in one where y is already a function of x, right? You got just y on one side equals an expression involving x on the right. What you can always do is just let your x be equal to t, and since you already know y is equal to 3x cubed minus 4 and x equals t, that means y can be equal to 3t cubed minus 4. Now that might seem like a silly problem, but I'm telling you it actually is a helpful idea to keep in mind as you move on in mathematics. There's going to be times where doing that will actually be helpful and convenient, right? But let's look at a more difficult one, parameterizing this one, this ellipse here, okay? This one, y is not a function of x, right? So we got to think about, okay, how can we write equations, so x equals and y equals, so that they satisfy this, okay? So one way to look at this is to say, we need to plug our equations, or our, I should say maybe expressions, for x and y in, and have this equal 1. I'm writing that out, and that might seem like, okay, yeah, you just wrote out what it means to have this equation. But here's the deal. We need to be able to plug things with t's in for x and y, and then those t's need to disappear. So what we might think about for a moment is, what relationship do we know of that allows me to square one thing and add it to the square of another and have it equaling just 1? Well, in this class, I hope that makes us think of our most important identity, the Pythagorean identity, right? So I'm going to tentatively put cosine here and sine here, with the idea that hopefully if I plug those in here, it'll behave like the Pythagorean identity and satisfy this equation. So let's just try this for a second. So if I say x squared over 4 plus y squared over 25, I need to be able to plug in my x and plug in my y and have it come out as 1 on the other side. But right now, that's not going to happen because I have this 4 down here and this 25 down here. So I know that the Pythagorean identity, writing this in red, right, would be cosine squared t plus sine squared t is equal to 1. It's only if you have cosine squared plus sine squared, no dividing by 4, no dividing by 5 or 25, you've got to just have this in order for 1 to pop out. So what we want to then think about is, what else could I do so that this 4 and this 25 get canceled? Well, if I stuck a 2 in front of the cosine and I stuck a 5 in front of the sine, then that means I would stick a 2 in front of this cosine and a 5 in front of this sine. And of course, if I do that, what happens is I get 4 cosine squared t over 4 plus 25 sine squared t over 25. Then those cancel, And then I do in fact have my Pythagorean identity. Which is going to just give me 1. So I have shown that this equation is satisfied when I plug 2 cosine t in for the x and 5 sine t in for the y. And so therefore that is going to be my proper equation. Now this one's a little tougher, so this might not be a bad one just to double check for ourselves, make sure we're doing this right. So make sure I'm in my parametric mode. And so I've got 2 cosine of t and then 5 sine of t. Oops. And let's go to my standard zoom here. Okay. Oops. There we go. And so in fact we do have an ellipse, okay? And we were expecting an ellipse for a couple reasons. One, you studied ellipses back in Math 141, and we know that that's an ellipse when you have x squared over a squared plus y squared over b squared equals 1. And also at the very beginning of our video here, right, looks a lot like this. And remember, a was number 4 here, where it was, you know, a number times a trig function for x and for y. So I think we can feel pretty good about that one. All right, now very last it says parameterize the line passing through 9, 7, and 6, 8. Okay, so this is kind of taking us back to a variation on an earlier problem we did. So definitely press pause on this one and give this one a try yourself. All right, now if I was to ask for the equation of a line and I gave you 2 points, you know, even before you took this class, just from your experience with algebra, hopefully the first thing you do is be to find the slope, right? So let's start by finding the slope of this line. So m is equal to, right, the change in y over the change in x, which is 1 over -3. But let's again remember, right, that's the change in y, that's the change in x. So when it comes to writing this down, we're going to say for x, we're going to have -3t, and for y, we're going to have plus t. Okay. So just taking the change in y and change in x and putting those as the coefficients in front of the t. And then what else do we need? We need an initial point. So here's the thing. You can use either one of these as initial points. So some people might put 9 here and 7 here, and that's great. Other people might choose to put 6 here and 8 here. And that's just fine too. It's no big deal at all. And so understand that all that's happening here is the starting place is different, but you get the exact same line no matter which one you choose. So if I go back into my y equals menu and then type in the first one, so 9 minus 3t, and 7 plus t. And what I want to do here is I'm going to go into Window, and I'm going to change my t step to be really small. And the reason I'm going to do this is so that you can really see this thing be graphed more slowly. And I don't know, let's go ahead and change the t values. Let's go like -5 to 5, for example. Actually, let's go from 0 to 5. I think that'll be good. So let's hit graph. Okay, and so we started right over here and then off it went. Okay, now if I go in my y equals menu and I put in the other version that we did, so we go 6 minus 3t and 8 plus t, and then I hit graph, notice what occurs there. I just started at a completely different spot. So the first one started here when I let t be 0 and went off that way, and then this one started here at t equals 0 and went off that way. Same line, just different starting spot.